ইলাস্টিসিটি তোদের অনেকেরই সিলেবাসে রয়েছে হাফিয়ারলি, তো আমি একখানা ইলাস্টিসিটি একখানা ব্রিফ ডিসকাশন করে দিচ্ছি এখানে। একটা শর্ট ডিসকাশন, যাতে মোটামুটি তোরা একখানা পরীক্ষা দেওয়ার মতো জায়গায় অ্যাটলিস্ট যাতে পৌঁছতে পারিস। ঠিক আছে? তাহলে ইলাস্টিসিটি প্রাইমারিলি কি? The property by virtue of which a body resists the deformation in shape or volume or both due to external forces acting on it. Okay, and this is the first part, and the second part is basically and regains back original shape or volume after the removal of this external force. Okay. This is called elasticity. এই ইলাস্টিসিটি কাকে বলে এটা বুঝতে পারলাম, যে কোনো একটা অবজেক্ট রয়েছে তাকে যদি আমি প্রাইমারিলি ডিফর্ম করার চেষ্টা করি, তো অ্যাট ফার্স্ট ইট উইল অপোজ দ্যাট ডিফর্মিং ফোর্স, বাট তারপরেও যদি তুই আরও লার্জার অ্যামাউন্ট অফ ফোর্স অ্যাপ্লাই করিস অ্যান্ড সামহাউ ইউ ম্যানেজ টু ডিফর্ম দ্য অবজেক্ট, তো যখন তুই ডিফর্মিং ফোর্সটাকে সরিয়ে নিবি, when you will withdraw the deforming force, the object will get back to its initial shape and size. That property is known as elasticity. তো এবার নর্মালি দেখ, স্টিল আর রাবার, এই দুটো জিনিসকে নিচ্ছি আমরা। এই দুটো জিনিসের মধ্যে আমাদের এখনও অবধি যা নলেজ আছে, সো ফার we have the knowledge of with the term is elasticity is familiar to us in terms of rubber, but the fact is that the steel is much more elastic than rubber. How it is so? So if there is a piece of steel out there and there is a piece of rubber out there, if I apply a force on it and consequently I am applying the same force on this one as well, I will expect less deformation in steel compared to rubber. Rubber will easily get deformed. So the primary fact you need to keep in your mind that resist the deformation in shape or volume. That is the primary fact. So as rubber is too reluctant to oppose the or resist the deforming force applied on it, so we will not call rubber as the elastic one. Steel is much more elastic for us. It has whenever you are applying any force on it, it's very difficult to deform primarily, and even if you somehow manage to deform it, then after the removal of the force, steel will get back to its initial shape and size mostly. But if you apply a large amount of force on it, then naturally it will get deformed permanently. We will talk about that later. So if someone asks us that which one is much more elastic, then steel is more elastic than rubber, because it opposes the deforming force which is trying to deform this object made of steel, whereas rubber opposes very feebly whenever a deforming force is applied on it. So rubber is very basically easy to deform, where steel is not. So that's why steel is more elastic than rubber. Okay. So, proceeding further, we will, based on elasticity, we can classify object into three different sections. The first one being elastic, the second one being plastic, the third one is elastomer. We will discuss these three cases. The elastic objects opposes the deforming force strongly and gets back its original shape and size after the removal of the deforming force. Okay, so when it comes to plastic objects, do not oppose at all. Never gets back into its original shape and size. And the third category being elastomer. Opposes feebly, opposes very little. Gets back to its original size after the removal of the force. Okay, so we have got three categories of materials: elastic, plastic and elastomer. Okay, so the basic example of elastic is basically all metals out there. You can call it steel or any other. Most of the metals are elastic by nature. Now plastic is basically, you can consider mud or even a dough, etc. They are very easy to mold actually, and they never get back to their initial shape and size. And the elastomer, well, in this category, our rubber lies. It do not opposes the deforming force, though after the removal of the deforming force, it gets back to its initial shape and size. So it is somewhere in between elastic and plastic nature of material. Okay. Now we will learn two basic terminologies of elasticity. They are stress and strain. Okay. So whenever we are basically concerned about stress and strain, we need to take care of a couple of facts. Now, what is stress? Stress is given by applied force divided by area of cross section of the body. Now the thing is that let us consider a cylinder. Okay, now if I apply a force on it, supposedly I am trying to elongate this cylinder. Now if I am applying force on it, these are my external force. After a certain point, I won't be able to extend it any further because an opposing force would have been developed inside the material. Okay, now this is the cross-sectional area of the sample, and now this force balances this external force. So this force balancing this external force, and this force multiplied to the per unit area actually. This force per unit area will give out the stress, the value of stress. So stress is equals to F by, if I consider the area to be A, then it's F by A. That is the amount of force acting per unit area within the material of the body. That is the force, the restoring force developed by the body. Okay, so make sure that this is not external force by unit area. The external force has been balanced by the internal force, that is the restoring force of the body, and as they are numerically equal, now we can call it stress is basically equals to F by A in short. But it is the internal force per unit area that opposes the externally applied force, so that the body tries to oppose any kind of deformation on it. So we will write over here, when a body gets deformed under the influence of external forces, a reaction force develops in the body because of elasticity. Okay, so this force is basically the restoring force. The restoring force. Now this force actually opposes the externally applied force, so that the body can avoid any deformation. Okay, now this force by unit area is called the stress. Is known as stress. Okay, so stress is basically force per area. So if you are eager to find out the dimension of stress, it is ml inverse t to the power minus 2, that is identical to the dimension of pressure. But remember, pressure is basically external force applied per unit area, and this is the internal force, the restoring force per unit area. They are mathematically, they look similar, dimensionally they are similar, even in terms of unit as well, but they represent different physical quantities. Okay, so now unit of stress. and that is Newton meter to the power minus 2. Okay. Now we will classify normal stress and shearing stress. Now if this one is a surface of a block, then a force which is basically applied on it like this, consider the force which is applied externally like this. Okay, so this force is practically balanced by stress developing in the opposite direction. So this stress can be splitted into two different sections. First one is this one and the second one is this one, where this one is called the normal stress, where this one is tangential or shearing stress. Okay, so this one is the stress which is balancing out the applied force. So the normal stress is nothing but acting perpendicular to the surface. Normal stress. And shearing stress is acting along the surface. That's all. Now if a force is such applied like if the force is a elongating one like this, then the stress developed within the body is actually called tensile stress. And the stress that has been developed due to compression is called compressive stress. The tensile stress looks like this, and compressive stress looks like this. The orange one are basically the stress, and the black ones are basically the forces applied on the body. Okay, now we will start strain. Now what is strain? It is basically ratio of deformation to the original physical dimension of the body. And that is, one can say, longitudinal strain, now what is it? If there was a cylinder or a wire of length L0, and now because of elongation it has been elongated like this by del L, then linear strain or longitudinal strain can be written as del L by L0. That is the deformation to the original physical dimension. Now there is volume strain as well. Consider for volume strain, there was a volume like this, and now it is basically looking like this. Okay. So this is the externally applied force on it. Externally applied forces are basically deforming the body. Its initial volume was V, and now it is V plus del V. So change in volume equals to del V. So therefore volume strain is equals to del V by V naught. Okay. So that is what we call volume strain. And now there is another kind of strain which is called shearing strain, but we will talk about that later. Okay. Now one can clearly visualize that the strain is basically ratio of two similar dimensional things. That means strain is dimensionless primarily, and quite naturally, as it is dimensionless, it is unitless as well. Okay. Now we will move to Hooke's law that involves the relation between stress and strain. Before going into that, I will try to discuss one basic thing. See, what develops first? A kind of question like Dimagena Murgia. The thing is that which one develops first in the body? Whether it is deformed at first and then stress develops, or when it is the stress develops at first but then the body deforms. Now, which one is the cause and which one is the outcome? Now, the thing is that whenever we apply force on the body, so practically we need to look towards the molecular theory at first. Supposedly these are basically group of atoms like this. This is the boundary of the substance or the material that we are dealing with. Now we have applied an external force like this, and under the influence of the external force, now these atoms which were separated by R0 beforehand, now they are coming closer to each other. They have been compressed. Now the separation in between them has decreased. Now because of that, they will definitely repel each other because their electronic clouds will repel each other. If you look towards an atom, it has the nucleus at the center and electronic cloud around it, right? So these electronic clouds will definitely repel each other, and thereby they develop this stress. Okay, so it is the deforming force at first which causes deformation in the body, which is known as strain, and then because of the strain the stress develops, which tries to oppose the external force and tries to regain its original shape and size. Understood? Now Hooke's law is stress proportional to strain. This is basically Hooke's law. The definition is basically within the elastic limit is proportional to strain. Okay. So we can write it as stress proportional to strain. Therefore, stress proportional to some constant. One can call it as E into, stress equals to some constant E into strain, that is stress by strain equals to E equals to elastic modulus. Now what is elastic modulus? That is the amount of stress developed in a body per unit strain. The amount of stress developed in a body per unit strain is defined as elastic modulus. Okay. Now one can clearly see that as strain is dimensionless, the dimension of elastic modulus is the dimension of stress. Therefore, the dimension of elastic modulus is m L inverse t to the power minus 2, and the unit is also Newton meter to the power minus 2. That's all. Now we can classify this elastic modulus into three different kinds of modulus that is within our syllabus. The first one being Young's modulus related to longitudinal strain, the second one being bulk modulus related to volume strain, and the third one being shear modulus or modulus of rigidity, that is due to shearing strain. Now we will discuss this. What is Young's modulus? Young's modulus longitudinal stress by longitudinal strain. Okay. Consider a cylindrical wire like this. Now, if I have applied some force on it and it has undergone some deformation like this, the initial length was L and the deformation is, consider the initial length to be capital L and the deformation is small l, then the applied force is this one, and so as the stress developed within the body F. Now this one has a cross sectional area, say A. So the stress is given by M by A, whereas the strain is given by small l by capital L. Okay. Now, therefore, Young's modulus Y equals to M by A divided by small l by capital L. That is F L by A L. This is Young's modulus. Now, as it is a cylindrical case, one can replace that. If I consider this one as the radius R, then one can also write that F times L into pi R square into L, that is a deformed area. Now it has the same dimension and unit as we have discussed in this case, as it is also an elastic modulus. It has the same dimension and same unit, which is Newton per meter square. Now proceeding to bulk modulus. What is bulk modulus? Now consider an object being compressed like this. Okay, being compressed like this, and the volume reduces. Say the entire volume of this sphere is V plus small v, and the volume of this sphere is only V. So the volume, there is a change in volume. So change in volume is small v, then definitely volume strain is equals to small v by capital V. Now volume stress, the volume stress is nothing but the applied force by area. In this case, this is basically force by pi r square, which is nothing but the pressure. Okay, so we have developed some pressure on the object, and now we can calculate the volume modulus of elasticity or bulk modulus. Therefore, bulk modulus K equals to volume stress by volume strain. Therefore, K is equals to volume stress is F by A, whereas volume strain is small v by V. So it turns out to be Fv, or one can write in the form of like now one needs to make sure that if I am applying pressure externally, then this change in volume is negative because the volume is decreasing. So this volume strain is negative as well. So we will write it like this. So it can be written as P minus of V by V. So it is actually PV by V. That is the pressure developed in terms of volume. Now in differential form, this one can be written as minus of V del P by del V, or minus of V dP by dV. This is the representation of bulk modulus. Bulk modulus can also be defined as the amount of volume stress developed in a body due to unit volume strain. Okay. So what does bulk modulus represent? See, the greater amount of stress required to deform the object means what? The object is much more rigid. Okay, so the bulk modulus represents the elasticity, that is denying any deformation under the influence of external force. How far an object can oppose that deforming force. Then definitely the reciprocal to this can be defined as a measure of how compressible an object is. If K represents how rigid an object is, then we can define a term which is known as compressibility, which shows compressibility equals to 1 by k, which represents nothing but how it is easy to compress an object. As k represents the rigidity, how elastic an object, so the reciprocal to k represents how easy it is to compress an object. So compressibility is inverse of bulk modulus, and that is given by this, and in the differential form it is minus dv by vdp. Okay, so compressibility is the factor by which we recognize an object as much more malleable or much more vulnerable to any kind of deformation, where k represents how sturdy the object is. The compressibility unit হচ্ছে ঠিক এর উল্টো, তো 1 by Newton meter to the power minus 2, that means meter square Newton inverse. K unit to same ही হবে, as it is also an elastic modulus, so it has got also the unit of the stress, which is Newton per meter square, and same dimension that of the stress. Now sharing modulus, bulk modulus হয়ে গেল, এবার sharing modulus ঠিক আছে। শেয়ারিং মডুলাস যদি আমরা ডিফাইন করি, কোনো একটা অবজেক্টকে কোনো একটা অবজেক্টকে যদি আমি একটা ট্যানজেনশিয়াল ফোর্স অ্যাপ্লাই করি, আমি যে ফোর্সটা অ্যাপ্লাই করছি, দ্যাট ফোর্স ইজ সামথিং লাইক দিস। A tangential force has been applied so that the object has undergone some deformation. Now, because of this deformation, this was the initial shape, and this is the final shape. We can do this with the cover of a matchbox. Now, if we are calculating, say this point is A, this point is A dash, this one is B, and this one is B dash, the angle being theta, the length, this one is L, and this length is small l. This point is D, and this point is C. Okay, so if this one is L, and this one is small l, sorry, this one is small l, then quite naturally this one has to be L plus small l. So this is the final length, and this was the initial length of the arm, which was previously AD, but now it is A dash D. Now if we consider the change in length, change in length is given by L plus L minus L, resulting into smaller. Okay, so strain or shearing strength is equals to small l by capital L. But from the geometry of the shape, one can say that small l by capital L is nothing but tan theta. If it is tan theta, then one can clearly say that as theta is very small, tan theta will tend to theta. So shearing strain turns out to be tan theta nearly theta equals to small l by capital L. Now shearing stress, if I consider the surface having an area A and the force is applied like this, then definitely the shearing stress is given as F by A. So the shear modulus eta is equals to F by A by theta equals to F by A theta. So this is the representation of shear modulus. Eta equals to F by A theta. Okay. Now shear modulus has the same dimension and unit as we have discussed earlier in this section. They have the same dimension and same unit as that we have discussed over here. All the three modulus of elasticity has the same dimension and unit. Okay. Now we will move towards Poisson's ratio. Now what is Poisson's ratio? It is the ratio of lateral strain to the longitudinal strain of a body. Now consider a cylinder like this. Now if I am elongating this one, then definitely it is going to be like this. Very difficult to draw. Now definitely if this one has got a diameter capital D, now this one will definitely get a diameter small d. If this one has got a length, say we can call it as capital L, then we can also say that the change in the diameter, if this one is length L, then we can call it L plus L, and this one is going to be D minus D. So as the volume remains constant of a body, whenever a body is elongated under the influence of some tensile stress, definitely as it gets stretched along its length, so definitely its cross section area will decrease, because the volume needs to be the same, no? as the density is not changing of the object, that means what, the amount of matter in the body is fixed. So if the length is getting elongated, then definitely its cross-sectional area will decrease. Now we are supposed to find out the lateral strain over here. Lateral strain is the change in the diameter, which is d by the original one, capital D, and the longitudinal strain is small l by capital L. So the Poisson's ratio sigma is basically d by capital D divided by L by capital L. So we can write d into L by L into d. This is basically Poisson's ratio. Now when it comes to Poisson's ratio, we need to take care of one fact, that it always appears in the form of a negative sign. We place a negative sign in front of it because either d by d is negative and L by L is positive, which is in this case, see the diameter has decreased, so the d, this small d is actually negative. So d by d is negative and the length has increased, so this small l is positive, so L by L is positive. If we compress the object, then definitely the length will decrease but the cross section area will increase. Then d by d will appear as positive and the small l by L will appear as negative. So one thing is clear from here, that sigma equals to the ratio of d by d and L by L is always turning out to be a negative one if we do not place a negative sign beforehand of it. So in order to make it a positive one, we place a negative sign so that it turns out to be positive. Clear? Because this term within the braces is already negative, so we have placed a negative sign beforehand of it so that it turns out to be positive. Now the range of sigma, mathematically it has a range -1 to +1/2, but physically it has a range 0 to +1. Okay. So why this range? Because it is impossible to find out any object which increases in length and cross section in both when a force is applied on it, or the converse, that decreases in length and in cross section both, as the amount of matter remains fixed. So definitely whenever we are applying some force on the object, as it is elongating, its cross section area must decrease, or if we compress the object, as it is contracting, its cross section area must increase. That is the fact. So range of sigma, the physical range being 0 to +1. We can calculate and we can show that even. Let L and R be the length and the radius of a circular cross section then the volume of the wire is definitely V equals to pi r square L. Now if we differentiate it on both sides, then dV equals to pi r square dl plus L into 2 pi r dr. Okay. we are taking differential on both sides. Where dV is the change in volume, dl is the change in length, and dr is the change in radius. Okay. Now, as we have talked before, that the volume is constant, amount of matter is fixed. As density is not changing, so we can say that the change in volume is 0. dV equals to 0. That means what? Pi r square dl equals to minus of 2 pi rl dr. That's what we have got from here. Now, we can rearrange these things. One r can be dropped from both sides and pi can be dropped as well. So, it's r dl minus 2 ldr. So we can take a ratio of dr by r, which is equals to minus of half dl by l. Now sigma is basically lateral strain by longitudinal strain. That means this one is dr by r minus of dr by r by dl by l. So from here we can get dr by r by dl by l equals to minus half. So minus of minus half turning out to be plus half. So sigma equals to 0.5. Okay. Now we will be calculating work done in stretching a wire. Now if we are about to calculate work done in stretching a wire, consider a wire of length say capital L, and it has been elongated by a length L under the influence of a force F, and the cross sectional area being A. Okay, or it is considered as alpha because we will consider the wire to be AB. So let us consider the cross section area to be alpha, and now Young's modulus is given by F by alpha L by L. That is the ratio of the deformation by the original length L by L. So this one turns out to be FL by alpha L. Okay, so the force can be written as Y alpha L by capital L. Okay, so this is the amount of force applied on the object. Now work done in deforming say dl length of the specimen, and that one is equals to dw f into dl, or y alpha by L LDL. Therefore, work done in total elongation L is W equals to integration dW, keeping aside y alpha by L, integrating LDL from 0 to L. So this one is going to turn out to be L square by 2, L square by 2. So if you have got this expression, so the work done turns out to be y alpha L square by twice L. Now we are about to rearrange this one. So W is equals to half into y L by L into the L is remaining out there and there is one alpha. So we need to rearrange this last time as well. So if we rearrange this one, then we can write it as alpha can be taken into consideration like in terms of force as well. So we can do one thing in order to rearrange this one. Let us write y alpha L square, and this one can be substituted in the form of let us keep that alpha L part, and we will introduce another L by L and we will be balancing it by alpha L. See, L square is there, L into L, L square. Over here we have introduced one extra L, we have balanced it out over here, and this alpha is this one, this y is this one, this 2 is over here as half. So this can be written as half into y into L by L. This term is nothing but the stress itself, because this one L by L is the strain multiplied to elastic moduli means what? It is stress. L by L is the strain itself, and alpha into capital L is the volume. Now work done per unit volume or energy density is equals to W by alpha capital L, that is the volume. So small w equals to W by alpha L, and that is given as half into stress into strain. আচ্ছা, এবার আমরা স্ট্রেস স্ট্রেন গ্রাফটা পড়ে নেব। দেখ, স্ট্রেস ভার্সেস স্ট্রেন যদি একটা ম্যাটেরিয়ালের জন্য, মেনলি ইলাস্টিক একখানা ম্যাটেরিয়ালের জন্য যদি আমরা প্লট করি, তাহলে এইরকম একখানা গ্রাফ দেখতে পাওয়া যায়। যদিও যে পয়েন্টগুলোর মধ্যে যে গ্যাপটা দেখিয়েছি আমি, এ বি সি ডি প্রত্যেকটা পয়েন্টের মধ্যে, দে মে অ্যাপিয়ার far separated from each other, but in actual they are very close to each other and very difficult to identify. যাই হোক, এই পার্টগুলো একটু এক্সপ্লেন করে দিই। দেখ, যে পয়েন্ট অফ দি আমরা ও এ পাচ্ছি, দ্যাট ইজ প্রপোর্শনাল লিমিট। আপ টু দিস লিমিট স্ট্রেস ইজ ডিরেক্টলি প্রপোর্শনাল টু স্ট্রেন অ্যান্ড দ্য বডি ইজ বিহেভিং পারফেক্টলি ইলাস্টিক। এই যে ও এটা ক্রস করার পর যে বি পার্টটা, এই বি পয়েন্টটা হচ্ছে ইলাস্টিক লিমিট, যার মধ্যে আমরা হুকস লকে এস্টাবলিশ করেছিলাম। এই এ থেকে বি পয়েন্টের মধ্যে আস্তে আস্তে স্ট্রেস প্রপোর্শনাল টু স্ট্রেন রিলেশনটা নষ্ট হয়, আর বি পয়েন্টে পর যদি বি পয়েন্টের পর যদি কোনো একটা অবজেক্টকে যদি আমি বি পয়েন্ট অবধি নিয়ে গিয়ে যদি আমি স্ট্রেসকে রিমুভ করে দিই, তাহলে ওটা আবার ও পয়েন্টেই ফেরত চলে আসে। মানে তার মধ্যে কোনো স্ট্রেন পার্মানেন্ট কোনো স্ট্রেন তৈরি হয় না, কোনো ডিফরমেশন পার্মানেন্ট তৈরি হয় না, অবজেক্ট আবার নিজের আগের জায়গায় ফেরত চলে আসে। কিন্তু যদি বি থেকে আমি পুশ করে অবজেক্টকে আরও বেশি স্ট্রেস ডেভেলপ করে যে সি পয়েন্টে মানে আপার ইয়েল্ড পয়েন্টে নিয়ে যাই, তাহলে তখন দেখা যায় যে প্লাস্টিক প্রপার্টি আস্তে আস্তে ইলাস্টিক প্রপার্টির উপর ডমিনেন্ট হয়ে যায়। খেয়াল করে দেখলে বোঝা যাবে যে সি থেকে ডি অবধি স্লোপটা নেগেটিভ। তার মানে সি পয়েন্ট ক্রস করে যাওয়ার পর যদি আমি স্ট্রেসকে কমিয়েও দিই, তখনও স্ট্রেন বাড়তেই থাকবে। সি থেকে দেখ ডি অবধি স্ট্রেস কমেছে, কিন্তু তাতে কিন্তু স্ট্রেন কমেনি, স্ট্রেন বাড়তেই থেকেছে। তার মানে প্লাস্টিসিটি চলে আসছে অবজেক্টের মধ্যে। এবার এই অবস্থায় যদি আমি আরও বেশি স্ট্রেস ডেভেলপ করি অবজেক্টের মধ্যে, তাহলে একটা সময় আসবে যে পয়েন্ট ই রিচ করে যাব আমরা। পয়েন্ট ইটাকে কী বলি আমরা? ব্রেকিং স্ট্রেস। মানে একটা অবজেক্ট এই পয়েন্টের পর ভেঙে যায়, ছিঁড়ে যায়। এবার এই পয়েন্টের পর ওয়ান্স ইউ হ্যাভ ক্রস দ্যাট ব্রেকিং স্ট্রেস, তারপর তুমি লোড রিমুভ করে নিলেও বা স্ট্রেস যদি কমিয়েও নাও, তাহলেও দেখা যাবে যে একটা পার্ট, যে কোনো একটা পার্ট অফ দি অবজেক্ট সেটা থিন হয়ে যাবে, এবং ওখান থেকে আস্তে 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 থিনিং হতে হতে ওই পয়েন্ট থেকে ছিঁড়ে যাবে বা ভেঙে যাবে অবজেক্টটা। পয়েন্ট এফটাকে হচ্ছে আমাদের পয়েন্ট অফ স্ন্যাপিং, মানে যে পয়েন্টে গিয়ে ছিঁড়ে যায়। এই সময় খেয়াল রাখতে হবে যে স্ট্রেসটা কমে যায় আস্তে আস্তে, কারণ এটা ইলংগেশন এত বেড়ে যায়, কারণ যে পয়েন্টটা থিনিং হচ্ছে সেটা তো কন্টিনিউয়াসলি লেন্থে বেড়ে যাচ্ছে। তো লেন্থে বেড়ে যাওয়ার জন্য স্ট্রেসটা ওই পয়েন্টে ফল করে, কিন্তু স্ট্রেস ফল করলেও ওয়ান্স ইউ হ্যাভ ক্রস দ্যাট পয়েন্ট ই, দেয়ার ইজ নো পয়েন্ট অফ রিটার্ন। অবজেক্ট অটোমেটিক্যালি পয়েন্ট এফ রিচ করে ওখান থেকে ছিঁড়ে বেরিয়ে যাবে। তো এইটাকে, এই যে পয়েন্ট ইটা যেটা, তাকে আমরা কি বলছি? ব্রেকিং স্ট্রেস। এবার এখানে খেয়াল রাখতে হবে সবসময় ব্রেকিং স্ট্রেস রিচ করলেই তবেই যে অবজেক্ট ছিঁড়ে যাবে এর কোনো মানে নেই। যেমন আমি বলছি যে একখানা ব্রিজ রেগুলার ইউজড হচ্ছে, ব্রিজেতে কয়েকশো টন গাড়ি চলাচল করছে, কিন্তু তাতে ব্রিজ ভাঙছে না, কারণ ব্রিজের ব্রেকিং স্ট্রেস এর থেকে বেশি। বাট স্টিল ইট নিডস সাম অ্যানুয়াল মেনটেনেন্স, আমরা অ্যানুয়ালি মেনটেন করি। আরও সোজাভাবে বললে পার্কে যে সুইংগুলো ঝোলে, দোলনা, সেই সুইংগুলোতে রেগুলার মেনটেনেন্স ইজ রিকোয়ার্ড। না হলে একটা পয়েন্টে দেখা যায় সুইংয়েতে রেগুলার বাচ্চারাই হয়তো দুলছে, কিন্তু সেই সময়তেও ভেঙে গেল। এর কারণ কি? যখন এটা ব্রিজ বা একটা সুইংয়েতে রেগুলার লোডিং আর আনলোডিং চলতে থাকে, লোডিং আনলোডিং বারবার 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 করলে পরে কি হয় যে অবজেক্টের হয়তো আমি ব্রেকিং স্ট্রেস রিচ করিনি, কিন্তু তা সত্ত্বেও দেখা যায় যে একটা এমন জিনিস চলে আসে অবজেক্টের মধ্যে যে কিছু কিছু পার্টে ওর দেখতে পাওয়া যায় যে পার্মানেন্ট ডিফর্মেশন চলে এসছে। পার্মানেন্ট ডিফর্মেশন মানে কিছু কিছু পার্ট, হয়তো একখানা চেন রয়েছে, লোহার একখানা চেন, সেই চেনের কোনো একটা পার্ট হয়তো থিন হয়ে যাচ্ছে। এবার যে পার্টটা থিন হয়ে যাচ্ছে সেই পার্টটা নিজের ইলাস্টিক প্রপার্টি হারিয়ে ফেলছে আস্তে আস্তে। এবার ওই পয়েন্টে অনেক সময় দেখা যায় যে ইভেন উইদিন দ্য ব্রেকিং স্ট্রেস, হয়তো ব্রেকিং স্ট্রেস আমি ক্রস করিনি, আমি সেরকম হেভিলি লোড করিনি, তার থেকে কম লোডেতেই ওই যে থিন হয়ে যাওয়া যে পার্টটা, ওই পার্টটা থেকে কী হলো, সঙ্গে সঙ্গে জিনিসটা ভেঙে গেল বা ছিঁড়ে গেল। রেগুলার ইউজেজ লোডিং আর আনলোডিংয়ের জন্য এই জিনিসটা হয়। এটার নাম হচ্ছে ইলাস্টিক ফ্যাটিগ। বই থেকে এটা ডেফিনেশন পড়ে নিবি সবাই, ইলাস্টিক ফ্যাটিগ। ঠিক আছে, এই পার্টটা কভার করে নিলে মোটামুটি আমাদের ইলাস্টিসিটি যা ছিল অন্তত পরীক্ষা দেওয়ার জন্য যেটুকু ভদ্রস্থ জায়গায় পৌঁছানো যায় সেটা আমরা কভার করে নিয়েছি। এবার বাকিটা তোরা মানে যখন আমি ক্লাসে রেগুলারলি পড়াবো রেগুলার টপিক হিসেবে, তখন ইন ডিটেলস ইন ডেপথ আমরা স্টাডি করবো।